Hello friends, welcome to another tutorial in electromagnetics and antennas. In this tutorial we'll talk about uniqueness theorem. If this is something that interests you, then please keep watching. The prerequisites to studying uniqueness theorem is the understanding of Laplacian equation and Poisson's equations. So let's get straight into this. This theorem is special in two aspects. The first one being the simplicity of its proof, and the second one being the difficulty in understanding its physical interpretation. So we'll talk about these two aspects in details. Now before we get to the proof of this theorem, I'd like to highlight a few key points of this theorem for better understanding of the physical interpretation. The first key point is that it provides a unique solution to the Laplacian equation. In other words, if you look at the Laplacian equation, which is a special case of Poisson's equation, which says Laplacian of v vector is 0, and its interpretation is Laplacian of potential is 0 for enclosed surface with no charge density. Now if we consider a closed surface with no charge density, rho v is 0. So according to Poisson's equation, we had Laplacian of v is equal to minus rho v upon epsilon naught. So this side of the equation vanishes, giving us the Laplacian equation, and the uniqueness theorem says that this Laplacian equation will have a unique solution. Now we need to understand what is the meaning of having a unique solution of this equation. To understand that, we have taken up this closed surface with no charge at all inside the surface. That could happen in two cases. The first case being that of the free space. If we have free space, we can assume that there is no charge, but then again we need to assume a hypothetical surface. So that's the limitation of free space if we want to consider rho v is equal to 0. And if we consider the case of conductor, we could have a definitive boundary or an enclosed surface, and the volume charge density inside the conductors is 0 because charge resides only on the surface of the conductors. So that will give me a clear-cut case of an enclosed surface with no charge density. However, both the cases are possible. So we'll look into both the cases while understanding its physical interpretation. And the solution to V is unique. That stems from Poisson's equation, as I mentioned earlier. The solution to the Laplacian equation are unique for a region, and there is no maxima and minima of potential at a given point. This mathematical operator, which is Laplacian v, is equivalent to 0, which we are saying that giving us a unique solution. This also represents mathematically that there are no maximas and minimas obtained out of this solution for v for a given point. That gets to our sixth key point, that there is no equilibrium point of charge potential in charge-free region, or it is tough to determine a fixed point of reference in free space. If we talk about the proof of this theorem, we need to first consider two solutions and then we'll prove it wrong. We are saying that the solution of this equation is unique, so we'll consider two solutions, v1 and v2, for this equation, and then we'll prove it wrong. And how do we do that? We assume this to be the solution. Del square v1 is equal to 0, del square v2 is equal to 0. So from these two we get 1 is equal to 2, and taking this on the left hand side gives me this. So this can only happen if v1 minus v2 is 0 or v1 is equal to v2 is equal to v. So that gives me the unique solution to this equation. Let us understand the physical interpretation of this. If you're considering a metal volume with certain surface, of course, with volume charge density is equal to 0, some voltage that is developed on the surface will be because of the external charges. So these charges are present outside the volume of the conductor. There is no inside charge present. Now if we assume that a potential or voltage V1 is developed on this side due to this charge, and V2 is developed on this side because of this charge, this is a wrong statement, because whatever potential is developed on the continuous surface of the conductor is distributed equally and is uniform, and we have a single potential at the boundary of the metallic surface or the conducting surface. That's the property of conducting surface, that the voltage is distributed uniformly along the surface of the metal. And we see that in numerous examples in semiconductor studies also, where when we study MOSFET, we have a layer of metal oxide where the voltage is uniformly distributed. So we cannot have two different voltages at the surface or at the boundary. We can have just one continuous voltage distributed at the surface or the boundary of the conducting material, which conforms to the uniqueness theorem. And the second point that I wish to highlight here is this one, that there is no equilibrium point for a charge potential in charge-free region, or there is no fixed reference point in free space. That stems from this argument that there is no maxima and minima, and we can graphically see that if we have this enclosed surface and if we keep our reference point inside this surface, we could see a maxima here because the curve has a shape like this. If we keep our reference point outside the surface, then this could represent a minima. So there is no fixed maxima and minima because of the absence of the reference point, and the point which is detained of any maxima and minima is known as a saddle point. So these two arguments are more than enough to understand the physical interpretation of uniqueness theorem, which conforms to both Laplacian equation and Poisson's equation. So I hope this tutorial was of help, and I've mentioned the key points here. If you wish to download this slide, you can go to my blog, and the proof is really simple. It's a two-step proof, but the physical interpretation is a little trickier. So you need to have a understanding of Maxwell's equations and the characteristics of charge in various media. Well, that's about it for today's tutorial. I'll see you in the next one. Take care. Have a good day and a good life ahead. Bye.